Okay, maybe we can start our last talk today. Our last talk is given by Péter Pál Pach from mathbb, Lendulitz Arithmetic Commentaries Research Group, Budapest University of Technology and Economics. He's also a Frontier of Science awardee for this year, and his talk is about progression-free sets. Let's welcome.
Thank you, and I would like to thank the organizers for organizing this event, which is going really well. So I will talk about progression-free sets on some joint work with Ernie Krut and Sevalev. I will start with the definition. In finite geometry, they say that a set is a cap if it does not contain three collinear points. So for instance, this curve is a cap because if you take any line, then there will be at most two intersection points. We will look at these gaps in some finite field setting. Specifically, in case of the field F3, if you look at the maximum size of caps in F3 to the n, then this question is usually referred to as the so-called cap set problem. This case, the choice of the three-element field is particularly nice because here the property that we do not have 3 points on a line, so the property that we are looking at a cap set is the same as we do not have lines because each affine line consists of 3 points. And here the lines are exactly the three-term arithmetic progressions. So in this setting, caps are the progression-free, three-term arithmetic progression-free sets. And in F3, so three elements form an arithmetic progression if they satisfy this equation. But if we are in F3, then -2 is the same as 1. So the equation of being a three-term arithmetic progression is already symmetric. So we can also say that a cap in this setting is a 0-3 sum-free set. And in finite geometry, they study frequently blocking sets. The complement of a cap set is a one blocking set because it needs to intersect every line. So the cap set problem asks for the largest possible size of a cap in F3 to the n. And even Tao mentioned at some point that it is one of his favorite open questions to understand the growth rate of this quantity. And as I have mentioned, some motivation is coming from finite geometry because the complement of a cap set is a blocking set. Another motivation is coming from number theory. So in number theory, giving good bounds for progression-free sets in the integers is a central topic. And this finite field setting serves as a model case for some of the techniques that can be applied in the integer setting. There are some connections with computer science and information theory as well. And since the formulation of the problem is so nice, there is a nice algebraic formula describing the condition that 3 points form a three-term arithmetic progression. It was expected that if this problem gets solved, then there will be further advances at related areas. So let me define. Three-term arithmetic progression is a collection of 3 points that are all distinct. We will look at this condition over the three-element field and also over Z4 as well. And in Z4, it could happen that these three numbers are not all the same, but the first and the last one is the same. So for now, let's say that three-term arithmetic progression is non-trivial if all these three numbers are different from each other. The question of progression-free sets was first studied in integers by Ross, who proved that they have zero density. And actually, the argument of Ross also gives a quantitative bound of the form n over log n. And there has been a long list of improvements by various mathematicians. Here is a list of some of them. But I mentioned just the current record, which is due to the breakthrough result of Kelly and Mecca, who gave such a Berentype bound for the maximal size of a progression-free set in the set of the first 10 positive integers. Before this bound, the previous best bounds were of the form n over log n, or n over log n to some exponent which is slightly larger than 1. So this jump from n over log n to 1 plus epsilon to this Berentype bound is a big improvement. Bloom and Sisesk's interpretation of the Kellner-Mecca proof improves this 1 over 12 to 1 over 11, but they had a further quantitative improvement, improving the exponent to 1 over 9. So still the same shape, just the exponent is better. So this was the integer case, and studying the question of progression-free sets in the integers is essentially the same as looking for the maximum possible size of a progression-free set in the cyclic group Zn. And it's quite natural to look at the question in other abelian groups as well. So for an abelian group G, let us say that let us use the notation that the size of the largest three-term arithmetic progression-free set is denoted by R3 of G, which is the standard notation. Determining R3 of Zn is roughly the same as determining the largest progression-free subset of 1 to n, but we will look at different settings when the group G is f3 to the n or z4 to the n. Let's start with the cap set problem case, f3. The very trivial bound is just the size of the group, but it's not easy to say something essentially better. Okay, maybe improving it by a factor 2/3 would be easy, because you can partition f3 to the n to the union of disjoint lines. From each line, you have to leave out one element, and this gives an improvement by a factor of 2/3. But already proving that they have zero density as the dimension grows is a non-trivial result. The first quantitative result was obtained by Meshulam, obtaining the bound 3 to the n divided by n. Actually, this type of bound is very similar to the best bound by that time in the integer setting, because what is this? The size of the group divided by the logarithm of the size of the group. In the integer setting, we also had bounds of the form n divided by log n, or later log n to 1 plus epsilon. So the bounds were of the same shape. And in 2012, Bateman and Katz had an improvement here, establishing the bound where the exponent here is not 1, but something slightly larger than 1. This positive epsilon can be explicitly given, but it's rather small. Let me mention some lower bounds. One possible way to get a lower bound for this quantity is the following. We look at the problem in a certain dimension. For instance, in dimension 1, we can take any 2 points, and we won't have three-term arithmetic progressions. And the observation is that if I have a progression-free subset, and I take the direct product of it with itself, I get a progression-free set in high dimension. So if I have a construction in small dimension, I can double it up, and I also get an asymptotic construction. So here from this bound, this trivial construction in dimension 1, we get the lower bound 2 to the n for every n. If we go to dimension 2, then the answer is still just the square of 2, no improvement, but already in 3 dimensions, the exact answer is not 8, but 9, which gives a better asymptotic improvement. This holds whenever n is divisible by 3, but if you add a minus little of n, then for every large enough n, you are fine. So if you want a general lower bound, it is enough to find a good construction in a certain dimension. The next case, the 4-dimensional case, was solved by Pellegrino. This is the case which corresponds to the card game set that you might know. Here the exact answer is 20, still better bound. And the exact values are known up to dimension 6. Here the situation is somewhat similar to the case of Ramsey numbers that was the topic of Jacques a few hours ago in the same room. It gets really difficult to get the exact values very soon. But the last lower bound is not coming from the 6-dimensional exact answer. Better constructions were found in higher dimensions, of course, without proving their optimality in that dimension. This was the bound of Kaderbank and Fishburne. Then Edel's construction, which was the record holder for almost 20 years, was coming from a construction in dimension 480. Recently, Tyrrell improved Edel's long-standing bound, and even more recently, Paredes with co-authors using large language models as well, improved Tyrrell's bound, but the best lower bound is still slightly better. It's a not yet published result of Naslund that there is a construction of size 2.2208, which slightly beats this AI-assisted previous record. So for finding lower bounds, Naslund's approach builds on graph capacities. Most of the constructions are coming from just finding one specific construction in one specific dimension. We will look at the problem in the case of Z4 to the n. It turns out that there are some differences between the odd case and the case when in this number here is divisible by 4. The case of f2 to the n is of course not interesting because in f2 to the n we do not have straight-line arithmetic progressions, non-trivial straight-line arithmetic progressions. So in the even case, the smallest interesting question is Z4. Here Lev proved a Schramm type bound, and here there was also an improvement by Sanders, but the improvement is smaller compared to the Bateman-Katz result, because here the additional factor is not n to the epsilon, just log n to the epsilon. And if the dimension is small, then the exact answer can be determined. But here the best lower bound construction is not coming from a concrete construction. It's of size 3 to the n divided by root of n. So in case of these problems, the main question was what is the right shape for the answer? Is the answer something similar to these bounds? These were the best bounds 8 years ago. So almost as large as the size of the group, only smaller by some polynomial or at least sub-exponential factor, or the answer is exponentially smaller. There have been mixed opinions and conjectures on this. And to answer this question, I forgot to mention that most of the results that I mentioned so far, the upper bounds, were obtained by Fourier analytic techniques, similarly to the integer setting. But it turned out that in this finite field setting, the right to rather be some polynomial technique. And to decide what is the right shape for this function, some polynomial idea was needed. And in the specific setting of Z4 to the n, the main lemma which makes it possible to answer this question has the following form. Although at other problems where the technique can also be used, the lemma has a very much different form, but let me explain the lemma in this setting. If we have a polynomial p with n variables over f2 with a certain degree d, and the subset of f2 to the n a, satisfying the condition that this polynomial p vanishes on the restricted subset a plus a. So whenever we add up two different elements from the set A, p P of A plus B should be 0, then we would like to say that if the set is large enough, and this is the threshold which we will find, then P also vanishes at 0, which corresponds to the case when we are adding up A with itself. So we would like to say that if the degree of the polynomial is small and the set is large, then if P vanishes on the restricted subset, then it also vanishes on the sum set. Here, in this case, the only difference is that the sum set also contains 0. We can think about it with the help of some rank of a matrix formulation. Let's define this matrix M, whose rows and columns are indexed by the elements of the set A, and the intersection of row X and column Y, we have the value P of X plus Y. So this is an N by A matrix. One can prove that if the polynomial has small degree, then the rank of this matrix is also small. But if the conditions of the lemma are satisfied, but the implication of the lemma is false, then this would mean that the matrix is diagonal. So its rank is just the size of the matrix, which means that if the size of the set is large enough, then the conclusion should be true. P has to vanish at 0. With the help of this lemma, with Kroot and Lev, we proved this exponentially smaller bound in case of Z4 to the N. And in less than a week after this result, Ellenberg and Geisweit, independently from each other, adopted the method to the capset problem as well. So in both cases, the answer is exponentially smaller than the size of the group. So this was in 2017, and till then, regarding the upper bounds, the only improvement is by a factor of root of n in case of f3 to the n. So the right constant in both cases is not yet known. There is a gap. In case of f3 to the n, there was an improvement by a root of n factor. And to show the proof, I will use a different formulation, which was given by Tao. So our original proof used the lemma that I just showed. Essentially, that lemma is the core of the proof. A few weeks after our results, Tao on his blog published a symmetric formulation of the technique, which makes it more clear how we make use of some rank behavior. In our original proof, we had some B-orthogonal systems of vectors. So already from the original proof, it's clear that some rank behavior plays a role. But in Tao's formulation, this will be much more clear. And it is also easier to apply this formulation in many settings. So let us define a new kind of rank for functions. Let's assume that we have some finite sets, S1, S2, Sk, and a field f. And f is a function from S1 cross S2 cross Sk to the field. To define a rank, we shall define the rank 1 functions. And in case of the slice rank, the rank 1 functions will be called slices. And a slice is a function which can be expressed in the following form. It is a product of a function depending on just one variable, and another function depending on the other variables. So if a function is of this form, then it is a slice. Its slice rank is 1. And here the index I can be anything between 1 and k. And now, since we defined the rank 1 functions, we can define the slice rank of every f. The slice rank of f is the smallest t, such that we can express f as a sum of t slices. So here the sets Si are all finite. And because of this, the slice rank is well defined, and it's a finite number for every function. For instance, if you take this polynomial, which is a sum of 4 monomials, then it can be seen that its slice rank is at most 2. In fact, it's exactly 2, but let's just say that it's at most 2, because we can use this rank 1 decomposition. Here, this is a slice, because the first factor depends only on x, and the second factor depends only on y and z, and the second sum is also a slice. Y squared depends only on y, and the other factor depends only on the other two variables. If we take x plus y plus z, then its slice rank is at most 3. Another example, because we can write p as a sum of 3 slices of the form 1 times x. Let's say 1 depends only on y, and then x depends only on x and z. But the slice rank of x plus y plus z is not 3. It's just 2, because there is a rank 1 decomposition using 2 slices only. So already, if we have 3 variables, then the slice rank will be something different from the usual rank. In 2 dimensions, the slice rank is just the same as the usual rank, but from dimension 3, the slice rank can be smaller than the usual rank. And let's see how can we use this new notion of rank to bound the size of cap sets in F3 to the n. In fact, there is no difference if we take any odd prime power q and look at the question in FQ to the n. The finite sets will be 3 copies of FQ to the n, and the field to which f assigns values will be FQ as well. And the function f will be the characteristic function of 3-term arithmetic progressions. If x, y, and z form a 3-term arithmetic progression in this order, then let us say that fxy is 1, so this is the Kronecker delta. And if x, y, z in this order is not a 3-term arithmetic progression, then f should be 0. We can write f as this polynomial, since if x, y, and z form a 3-term arithmetic progression, then xi minus 2yi plus zi is always 0. So here we have a product of 1s, which is indeed a 1. If x, y, and z do not form a 3-term arithmetic progression, then there is at least one coordinate where xi minus 2yi plus zi is different from 0. But if we raise this non-zero number to the q minus first power, we get a 1. There will be a 0 factor in the product, and the whole product is 0. Okay, so this is the function f. We have a set A, which does not contain any 3-term arithmetic progression, and our goal is to bound the size of this set. First, we claim that the size of the set A is nothing else but the slice rank of f being restricted to A times A times A. Why does this hold? This holds because it can be proved that the slice rank of a diagonal hypermatrix is nothing else but the number of non-zero entries on its main diagonal. For the usual rank in 2 dimensions, it's a triviality that if you have a diagonal matrix, then its rank is the number of non-zero entries on the main diagonal. For the slice rank in higher dimension, it's not a priori clear that this should hold, but it can be proved by using an inductive argument and playing with orthogonality. So if you have a diagonal hypermatrix, then the slice rank is just the number of non-zero entries on the main diagonal. And if A is progression free, then if we restrict F to A cross A, then this is a diagonal hypermatrix. On the main diagonal, we do have non-zero values because of the constant 3-term arithmetic progression. For any element of A, the values A, and A form a trivial 3-term arithmetic progression. So on the main diagonal, we have some non-zero values. In fact, for any element of A, we have one such element. But outside the diagonal, there are no non-zero values, so it's diagonal. And this means that to bound the size of the set A, it suffices to bound the slice rank of F restricted to A cross A. It's perfectly clear that if we do not restrict F, then the slice rank is either the same or something even larger. So bounding the slice rank of f is enough. And it can be proved that the slice rank of this function f is at most cq to the n, with a constant cq being smaller than q, because of the following. So we have this product. This gives us a polynomial of degree n times q minus 1. Each monomial appearing in this polynomial is a product of some x's, some y's, and some z's. Now let's look at the total degree in the x's, the sum of the alpha exponents, the total degree in the y's, the total degree in the z's. And we will look at the minimum sum. And the minimum of these three sums will be at most the third of the total degree of f, which is n times q minus 1 divided by 3. And we can do the following. We can group the monomials at the part where we have the smallest sum. So let's assume that for this monomial, the sum of the alpha exponents is the smallest one. Then we will have a slice in which the factor depending on x is x1 to the alpha 1 times x2 to the alpha 2 times xn to the alpha n, and we collect all the other sums that we need at this monomial of the x's. We haven't collected everything because it might be the case that in some of the monomials the smallest the sum of the alpha exponents is not below this threshold, but we do the same with the monomials of y up to degree n times q minus 1 divided by 3, excluding the ones that we collected before, and also for z. And this gives a bound for the slice rank that the slice rank is at most 3 times the number of such n tuples where each alpha I is between 0 and q minus 1. We are over fq, so we might assume that all the exponents that we see are less than q, since if we see an exponent which is larger than q, then we can decrease it by q minus 1, where the total degree is at most n times q minus 1 divided by 3. And if we take a random n tuple in 0 q minus 1 to the n, then the expected value of the sum would be n times q minus 1 divided by 2. And this is below the expected value. So the number of such n tuples is exponentially smaller than q to the n, using some easy probability theory. In fact, formula can be given for the CQ obtained from this argument. So this is the way we use the technique in case of the CAPSAT problem. Another application is about sunflower free sets. We say that a collection of k sets is a sunflower if the intersection of any two such sets from the collection is the same. We will look at the case when k is equal to 3. So sunflowers with 3 petals, 3 sets, intersection of any two is the same here in the middle. And the conjecture of Erdős and Szemerédi states that if we have a k sunflower free subfamily, a family of subsets of an n element set, then the number of sets contained in this family is exponentially smaller than the total number of subsets. This is a conjecture for every value of k, at least 3. And with the help of the previous technique, the case k equals 3 can be solved. So from now, instead of saying 3 sunflower, I will just say sunflower, because this is the case where we have some implications. Already before this new result in 2013, it was proved by Alon, Spilka, and Umans that there is a connection between the CAPSAT problem and the Erdős-Szemerédi sunflower problem with k equals 3. Namely, if there is an exponentially small CAPSAT bound, then there is an exponentially small bound for the sunflower problem for 3 sunflowers. And they made it quantitative. If you put in the Ellenberg-Geist weight constant to the result of Allon-Spielke and Ullmann's. Then you get the bound 1.94 to the n. But a few hours after Tao's blog post on the slice strength method, Naslund and Savin give a better bound, where instead of using just the result, they use the technique itself, and this provides a better bound. So how can we use this technique for bounding the size of sunflower free family subsets of sets? It's quite natural to think of subsets as characteristic vectors. So now to a sunflower free family F, we can assign a subset of 0, 1 to the n. To each set, we assign its characteristic vector. And the function t, whose slice rank will be used, is the following. It's defined on the product of 3 copies of 0, 1 to the n. And for the field, we can choose, for instance, the real field. And the observation is that if we have a sunflower, a 3 sunflower, then in the middle, the points are contained in 3 of the subsets. In the petals, they are contained in just one subset, outside the sunflower in none of the subsets, but no point is contained in exactly two subsets. So we shall take the polynomial t this way, because then if we have a sunflower free family set, then if we take 3 different vectors x, y, z from the set S, then this product will be 0 if the family is in this sunflower free. If x, y, z are all the same, then we won't have any 0 factor, so we will get a non-zero value. But there is a slight problem, because if we talk about 3 vectors, then there is a third case. So they are all equal, they are all distinct, or 2 of them are equal, but the third one is different from them. And in this case, which is outside the diagonal of this tensor, we could also get non-zero products if we are in this situation. So if we take 2 copies of this set, B and C are the same, and there is a superset of B and C, then here the points are contained in 3 sets, here in just 1, and outside nothing. But we can solve this issue by restricting the size of the sets, the Hamming weight of the vectors, which will add just a polynomial factor to the resulting bound. Because if we assume that in the set S, all the vectors have the same Hamming weight, then it will be inclusion free. Sorry? This sunflower bound. And which lemma? Say it again. I know about only this proof for maybe someone. Yeah. So fixing the Hamming weight, the sunflower family set will also become inclusion free, and in this inclusion free case, this T will be a diagonal tensor. So the size of the set SL, where the Hamming weight is fixed to be L, is the same as the slice rank, and we can bound the slice rank in the same way as we did before. So here the existence of trivial sunflowers and the trivial return arithmetic progressions are somewhat needed to be able to say that the size of the set is the same as the slice rank restricted to the corresponding product. Okay, getting back to progression-free sets. In general, of course, it's an interesting question to determine the quantity R, K, Z, M to the N in the general setting, but the question seems to be rather difficult. So in the case of progressions of length 3, in the cases 3 and 4, These are the best bounds right now. And from these two cases, in fact, looking at the case 3 or the case of any odd prime is essentially the same. It is not difficult to also prove that for any number m, which is larger than 2, there is an exponentially small bound. But if you look at longer forbidden arithmetic progressions, where the length of the forbidden arithmetic progression is at least 4, then it is not known in almost any of the cases whether the answer is something exponentially small or not, except one tiny class when m is divisible by 6, and the length of the forbidden arithmetic progression is at most 6. And just to illustrate how we get these exponentially small bounds for composite m, for instance, if you take z15 to the n, then inside z15 to the n, you have a subgroup isomorphic to z3 to the n, which has 5 to the n many cosets. From the additive point of view, these cosets are isomorphic to each other. In each of the 5 to the n cosets, you can apply the capset bound. And since in case of z3 to the n, there is an exponentially small bound, applying it in all of the cosets, you get an exponentially small bound for z15 to the n. So these are the easy implications. If you take a prime power like z9 to the n, then this trivial implication would give this constant, although by several groups a better bound was obtained by using the technique and not just this easy reduction idea. In the even case, such an improvement was also done for z8 to the n by Petrov and Poholta. Here the trivial implication would be this constant, but they proved a better bound. Now, if the number m has residue 2 mod 4, then it turns out that we get back the odd case. So between the odd cases and the cases when m has residue 2 mod 4, there is no difference. The case when m is divisible by 4 is slightly different from these. So let's take a look at the case of z6 to the n, which is somewhat special because of the special structure of z6. The reason behind this is that the prime factors of z6 are too small. So only the structure of z6 makes it possible to prove exponentially small bounds right now. So about R6, Z6 to the n, the main question would be, of course, to decide whether it's 6 or something smaller than 6. But interestingly, it is not even clear that this limit exists. If the length of the forbidden arithmetic progression is 3, or if the number m is a prime power, then it's clear that the corresponding limit exists because we have the product construction. If you have a construction in a certain dimension, then you can bubble it up. And from this, it easily follows that the limit exists. But in the setting of z6 to the n, R6, z6 to the n, the product construction does not work. Already, if you take a 5-element set in dimension 1, and you take the direct product of it with itself, then there will be a 6-term arithmetic progression consisting of different values, different elements. So the product construction fails to work here, and somewhat surprisingly, we could not prove that this limit exists. But if it exists, it turns out to be less than 6. But let's look at the case of small dimensions first to get familiar with Z6. So the next case would be the 2-dimensional one. And here the answer turns out to be 25, although the construction is not the trivial one, as we might have expected. And in case of Z6 to the n, a certain reformulation of the problem turns out to be really useful. Let's consider the following question. We have 2 to the n subsets of Z3 to the n, such that these subsets satisfy the condition that although they can contain 3-term arithmetic progressions, but no 3-term arithmetic progression can be contained in at least two of these subsets. And we are interested in the maximal total size of these subsets, And it can be proved that the answer is R6 Z6 to the n. So instead of looking at 6-term arithmetic progression-free subsets of Z6 to the n, we can look at a family of subsets of Z3 to the n that can contain 3-term arithmetic progression, but no 3AP can be contained in 2 of these. In a 2-dimensional case, we have 4 subsets. And here is a construction of size 25. As you can see, we indeed have some lines contained in these sets, but no line is contained in 2 of the subsets, and the total size is 25. So this is the lower bound, but how can we prove an upper bound? If we know the size of the set, then we can determine the smallest possible number of 3-term arithmetic progressions that must be contained in the set. Up to size 4, we can avoid arithmetic progressions. At 5, there will be at least one 3-term arithmetic progression. If we take all the points, then we get all the arithmetic progressions, and it is not difficult to fill in the rest of the values as well. But then we can formulate an integer program as follows. Xi denotes the number of I-element subsets. We know that we have 4 subsets. Altogether in Z3 squared, there are 12 3-term arithmetic progressions. And since each of them can be contained in at most one of the 4 subsets, the total number of 3-term arithmetic progressions that must be contained in these 4 subsets cannot exceed 12. Since otherwise, by pigeonhole principle, there will be a 3-term arithmetic progression which is contained in at least 2 of these subsets. And the solution of this integer program is 25, so which proves the optimality. And it can be also proved that the construction is unique in some reasonably defined sense. So here, although the product construction fails to work, the answer is still 25. But if we go up to dimension 3, the answer is smaller than the third power of 5. So it's not just the product construction is not working. The actual answer that we don't know is also smaller than the third power of 5. And the same idea can be used to get asymptotic upper bounds that are exponentially smaller than 6 to the n. To achieve these bounds, one should use the previous idea and a supersaturation extension of the cap set result, stating that if you have a very large subset of Z3 to the n, then it can also be proved that you will have a lot of 3-term arithmetic progressions. So according to the Eilenberg-Geisfeld bound, if you have a set of size 2.76 to the n, then you have at least one 3-term arithmetic progression. But this supersaturation extension gives that if you have a set of size 2.999 to the n, then you have exponentially many 3-term arithmetic progressions. But if the number of arithmetic progressions contained in these 2 to the n many subsets exceeds the total number of 3-term arithmetic progressions in these 3 to the n, then the condition will fail to hold. And if you put this together quantitatively, this gives this bound. We gave another bound with Palinca in terms of the value of R3 Z3 to the n. If here we plug in the best bound for cap sets, then we get a worse constant. But if the cap set bound gets improved, then the second bound might beat the first one. And we have just the trivial lower bound. And to conclude my talk, I just show a summary about the shape of the answer. So now it's known that for 3-term arithmetic progressions, the answer is always exponentially small. The answer is also exponentially small if the length of the forbidden arithmetic progression is larger than 3 but not larger than 6. There is no other example known when the answer is known to be exponentially small. And interestingly, there is no case known when the answer is known to be not exponentially smaller than the size of the group. And I finish here. Thank you.
Okay, thanks for a wonderful talk. Now questions?
So do you expect any examples when it's not exponentially small?
Actually, maybe I do not.
Right, I don't know.
So I would put my word that everything should be here. But yeah, finding any new result here or there would be extremely interesting. But in order to do so you have to do it for a prime power for length 4 in this case, or find a large construction in the other case that might not exist. We'll see, or we'll not see.
Any other questions?
Are there any other configurations, but maybe higher dimensional that have been studied or interesting?
Sorry, other?
Yeah. Are there any higher dimensional configurations? So maybe it's 4 points that satisfy certain linear relations?
So other configuration, yes. So you mean instead of arithmetic progressions, looking at other configurations, right? For instance, corners, when you have 3 points this way in say fp to the n cross fp to the n, is also an interesting question, which is in some sense on the reach of the boundary, is on the boundary of the current techniques, because if you try to use the slice rank technique for 4 progressions, then you don't get a non-trivial bound, but doing anything better would help. And in case of corners, this is also the case. If you apply this slice rank technique in a naive way, then the resulting bound is trivial, but just slightly trivial. An exponential improvement of the resulting bound would help. Yes, so it's there are other configurations of interest. Yes.
Now, any other questions? If not, let's thank our speaker again.
Thank you.
This is the end of this afternoon section.